Okay, so we will continue our discussion about linear regression, okay, the machine learning for linear regression. And the last class, I believe we already discussed quite a lot on linear regression with gradient descent, okay, with gradient descent. And also just keep that in mind. Linear regression is about continuous target value, okay, not like perceptron add line. Those two are for classification. So it's for discrete value, okay, so that's a difference. And so regarding gradient descent, so here this diagram shows we consider just a single feature. Okay, and because like a single feature, and we assume like the theta zero as zero, okay, and then we just consider the single weight basically. It's match that weight. So here it's also single weight, and this is regarding, so this basically is W. So this JW is a cost function. And just a quick review, cost function is not exactly a sum of square error, okay, but it's mostly come from the square of sum of the square of error. And so the gradient descent, the basic concept is you start with some initialized weights, is it? And then you keep updating the weights. And when you do the update of the weights, it depends on the derivative of the cost function regarding the weight, okay? And then you update the weights, so that's, and then we need to also consider the learning rate. The learning rate. So then, so assuming like it's start at this, so this is the initialized weight, okay, and then you keep updating it, so it's going to getting close to the minimized cost. Then when we find some values that close to the minimized cost function, then that weight, so this weight is the optimal one. Then you can use this weight to construct your linear regression function, okay? So that's the general idea, or you choose from the other side as getting close. And we also discussed the learning rate, not too large and not too small, the benefits. And for this, for the above diagram, because it's just a quadratic expression, basically, is it the cost function regarding the weight. So it's just a quadratic expression, is it? And from math, you know how to find the minimum value with a function, is it? So we take a derivative and set it to 0, is it? And then you solve this equation. And if it involves multiple variables, then you need to solve the simultaneous equations, is it? So we can also analytically solve for the W, is it, from math. So then the question is, why don't we use the math analytical way? Is it, why do we need to use gradient descent. Is it? So for the okay, so for the so here is regarding like the cost function regarding M features. So this is regarding M features. That is the cost function, okay? And so this is our hypothesis. This hypothesis is a linear. Okay, it's a linear function regarding the W, that is regarding the weights. So the cost function itself, the weights is unknown. So if we do analytically, then you take a derivative regarding each of the weight, is it? And then you set it to 0, okay? And because in this case, it's multiple unknown variables, is it? So basically it's a simultaneous equation. Then you need to solve it to find W0, W1, all the way to Wn should be, okay. So that's regarding the analytical way. And then let's see. And then over here, over here, so we have multiple samples. So here we have M samples. Okay, M samples, and so if you also have the number of features, is it? And so the expression that we will solve based on the previous one, it's a big, a huge matrix, is it? So each individual one can be expressed like this, and regarding all of the samples, then it's going to be a huge matrix, is that a huge matrix? And so from mass, so basically the weight then can be, so that's not a very difficult task, okay, to derive this relationship, is it? Regarding the features and the target values of the weight to solve this cost function regarding each of the weight, is it? And we can find the weight expression can be expressed like this, and all this expressed is a matrix expression. So over here for this part, then it involves the inversion of huge matrix, because this X matrix, the sample size can also be huge, is it? Not just as maybe tens of thousands or maybe millions of samples, is it? And the feature, it can also go very large. Later on, we will see, like if you think about like image, that there are the feature size is also going to be quite large. So if we purely wanted to do the analytical way, like the inversion of the matrix, then it's going, so some of the case, it may even not have solution, okay? And most of the time, it may also be very slow. So basically over here, what we want to discuss is the comparison between gradient descent and the analytical way to solve the normal equation. Is it? For gradient descent, then we need to choose the learning rate. And then it involves many number of iterations. So in our program, we call it each of the epochs, is it? And if you recall, generally speaking, the cost function, is it the arrow of the arrow Oh, also, yeah, basically it's a cost function here. So the cost function, and here is the epoch, is it? So with each iteration, is that each of the iteration, the value should also decrease the cost, is it? Then that means you are on track for the learning. So for the gradient descent, even though it may need many iterations, but it overall works well, even when the feature is large, okay? But a comparison with the analytical way, then we don't need, so there is no need for learning rate, okay? And there is no need to do iteration, so no number of epochs, okay? But you do need to calculate the big matrix, okay? And algorithm they analyze is going to be order of n squared. So we can clearly say algorithmically it's also not efficient, is it? And also if n is very large, then it's going to be quite slow. And there is some other scenario is the analytically regarding the normal equation, it's also may not be inverted, is it? So for this part, it may not be invertible. If it's not invertible, then there is no solution, is it? If you want to do analytical way, will that be possible to happen? And it is it? Sometimes you have redundant features and they are linearly basically dependent, is it? So like the house price prediction, is it? And if you pick the features like size in square foot and size in meters, basically these two features, it's linear dependent, is it? Then if you want to, you pick like these two as two different features, and when you try to calculate the inversion of the matrix, then it's non-invertible, okay? So that's maybe a case. And the other case is you may have too many features, okay? And later on, we will also see when too many features, then sometimes it causes a lot of noise, is it? So that's the case is the number of samples is even less than the number of features. Okay, number of features. Then in this case, you may not also be able to find a solution analytical way. Okay, but of course there are some ways to get around. Also for machine learning is how do we reduce the number of features, and we can also use some technique we call regularization. Okay, so later on we will learn the technique. So that's the general idea. And next, so we finish the discussion about the theoretical background of the gradient descent for linear regression. So what next? So let's take a look let's take a look at the examples. Let's see which example we start first. Okay. So here, okay, we will first start with univariable linear regression. Okay. And on our course website, and the data file we also provided, and of course you need to import the respective libraries. Okay, NumPy, pandas here, and this is for plotting. Okay, we briefly discussed. So here is a pretty simple data file. Okay, CSV file, and here we have the glimpse of the data it looks like. Okay, so it has just basically it's just some numbers we have over here. And here it also, so total we have 97 samples, okay. So anyway, so that's just some numbers. And regarding the relationship between these two, so we have first column of data, second column of data, etc. And basically, what over here to describe is regarding it's regarding the population of some city, okay, and the profit, okay, the profit. And over here, let's see. So we have this data, is it? So this is the first column, and this is the second column. And basically over here, you pick one as a feature and the other one as the target value, is it? And we try to find the relationship between Y and X. So between the target value and the features. And over here, the feature is the population. And here the Y is the profit. So we try to find a linear relationship between the profit and the population. So based on population, can we predict some close profit? So that's based on this set of data, okay. So the first step over here, we just do some scattered plotting, okay. So we have these two values. And so over here, we also specify the ticks, okay, for the X and Y axis. And the label we also provide, is it, and the title. So this is scattered plotting. So all of the sample data is plotted here, okay. So it's regarding population and the profit. Okay, so that's regarding the data. So after we get the data, if you recall previously, so in sklearn, the first step that we do is we split the data into training and testing into these two different sets, okay? And here we take 90%. So 90% for training. And 10% is for testing. Okay. And if you call this model, it will automatically take care of the splitting of training and testing data, okay, for us. So that's not a big issue, okay? And because over here, generally speaking, if you recall, the first step is split the training and the testing. And then generally speaking is next, we need to do feature scaling. And over here, if you recall, the data size are pretty in the same scaling range. So we kind of skip that step, okay? So then we directly do the model training. We move to model training. And here we are going to do linear regression, okay, linear regression. The detailed explanation, you can find it from the sklearn official website, okay, give us a lot of detailed expression. So the first step to do the learning is you need to create an object of the linear regression. So we create it. And also over here, we needed to be careful is that linear regression does not take a one-dimensional array, okay? So we need to do reshape of our previous the data from one-dimensional to kind of to two-dimensional. Because over here it says the shape of the data should be number of samples and the number of features. Okay. And over here, we just have a single feature. Is it one feature population? Is it population? And how do we do for the training and testing data? So we get their values and we call the reshape. Is it? And with this reshape, it's a two-dimensional, from one dimension to two dimension. Is it? So it's a reshape from one dimension. You have one dimension to the two dimension. Okay. So over here we have this negative value. Okay. So the negative value from the NumPy packages, it gives a new shape parameter. Okay. So it depends. So anyway, so that means for the second dimension, because over here we just have a single feature, is it? So only one column, is it? And for the number of rows, then it depends on all of the data. So that's what this -1 means. Okay. If you recall previously from NumPy, we also have some new axis. Okay, so here just we can also use this -1 for the reshape method. And the same thing for testing data, you also need to do reshape. Okay, so after we reshape the data, then you can call the fit. Okay, the linear regressions models fit method. So if you recall, so far for no matter it's a perceptron or linear regression from SK, it's always, when you do training, you always call the fit. Okay, and your fit, you have the model. Okay, be trained. And because over here it involves linear regression, is it? So for linear regression, basically it's the slope and the intercept, is it? And you can also get the intercept and the slopes value, okay, through the model dot intercept, model dot coefficient. Okay, you can also have the value. And then you can predict with the testing data. So when you call predict, you plug in with testing data. And then you can, if normally we care about the accuracy. So models accuracy, is it? So for sklearn, you can just directly call the models data score, is it? Then you plug in the testing data of its features and the target values, is it? That will tell you the accuracy. So in this case, it's around 93.5%. So it's a good accuracy. And then we can also, so what is the next one try to show is you can predict this y as a predictive value. You can also find the testing part of the target values mean, is it, with NumPy's mean. And we can also find standard deviation, is it? And then what over here is we try to find how many testing and the prediction are not the same, doesn't match, is it? Then you can call the sum, is it? And totally in this case is 10. And what this part try to show is, so total number of the values, is it? The predicted value, it's in certain range, is it? The range based on the predicted, so one standard deviation, is it, from the predicted value. And so how many will fall within certain range? So basically over here, it's one standard deviation, is it? And here it also tells us this 10. So it's just, we can collect more performance related metrics, okay? And what the next part try to show over here is we continue to do predict. Then this time, this just maybe some future sample that you collected, or just you're going to use this as for your applications, and then you have new data, and then you want to predict, is it? So here we have this two new population, and then we want to predict what the profit is. Is it? So then in this case, same thing, then you need to reshape, okay, for this data. Because over here it's a profit at a certain, $10,000 range. That's why over here you times the $10,000, okay. So then we can get to the profit, okay. So this is, once you make sure the model that you think it's acceptable, then you can use it to do the new prediction. So of this example, this part discussed using sklearn, okay, using sklearn. And for the remaining part of this example, it discusses the detailed raw implementation of the cost function. So compute cost, okay. So this is the raw implementation, and it's just for reference, okay. So if you're interested, and you can take a close look. So we are not going to go to the detailed discussion, but anyway, so here it provides a cost function, okay, in this specific case, okay. And then we can, so based on what the data is it, so our data, the previous univariable data, then we can also call the computer cost, is it, with certain learning rate, okay. So it gives us the cost. And what the next part is to show the raw gradient descent function, okay, raw gradient descent. So because it's gradient descent, so it involves a number of iterations, is it? But from this raw implementation of gradient descent, you can also collect the learning rate and the cost history, okay. This cost history is based on the number of iterations. Okay. And also you can also find the corresponding, like oh, I'm sorry, I got messed up. This theta is our weight, okay. So in this case, from this gradient descent, it gives you the cost, the history of the cost function for each iteration, and it also gave us the finalized weight, okay. And once you have the weight, then we know the linear hypothesis function, is it? So this is the raw approach. For the raw approach, and what it can benefit is with sklearn, we don't know. So it didn't provide us, so we don't know the cost function versus the iteration. So that's kind of in a black box. You cannot find the relationship between this, between the cost function and the iteration. So it doesn't provide that data. And so, but a lot of times you may want to visualize the relationship, is it, between the cost function and and also the not just the iteration, that, and also you want to know the relationship between the cost function and the weight. So here's regarding the weight, is it? And if you recall back, is it, recall back? So the generally for one dimensional, it's a convex. So convex function, is it, for the cost function. And here we can see, because we have we have W0 and W1, is it? We want to know the relationship of the cost function. So this is a 3-dimensional. So the 3rd dimensional is regarding the cost, regarding the cost function. So here it also plot so visualize, show us the relationship between the cost and the weight. Because we have this gradient descent calculation, is it, that compute. So you can do the plotting. And as to how to do this plotting, and if you're interested, after class, you can also take a look, okay? So based on what we previously briefly discussed regarding plotting, and you may also need to do a little bit of research more about a couple of functions, plotting related functions, okay? Okay, so that's regarding the contour plotting. You can also borrow that code, okay, if you like. And what the next one shows us is the cost functions using gradient descent versus the number of iterations, is it? And then in this case, we can clearly see this training model so is on track. Is it because the cost is decreased with the increasing of the number of iteration, and at a certain point, then the value changes very small, is it? So this represents its convergence. Because previously we discussed the gradient descent, you needed to make sure it's converged, is it? For learning rate, if you recall, if it is too large, then it's called overshooting, is it? Then for overshooting, then the relationship is not going to be like this. Okay, so it may go too small and then go back to large, is it? So then that's not on track. But regarding the cost function and the number of iterations, if you wanted to make sure that your model is on track, then this is supposed to be the relationship. Okay, so this is regarding cost, and we can also, because we know the weight, the optimal weight is this, so we can also plot the line, we call it a line of the best fit, is it? So this is a line of the best fit, is it? All over here, it's regarding samples, is it? And the cost is based on the offset between the real sample values and the best fit line. Okay, so that's regarding, and also you can do predict after you come up with the weight. So that's an example for union variate. Okay, what is the next one in this example is multivariable linear regression. Okay, it also support. So over here we have 2 features and 1 target, is it? So 2 features and 1 target. So you're going to extract the features and the target value. And number of samples size is not big, okay? And then in this case, we are going to still using sklearn, okay, sklearn. So we are going to collect the feature value, okay? And of course, you also want to know the number of samples. So the feature value then, in this case, it's the first 2 columns is regarding feature. The last column is for the target, is it? And the same thing, you also need to make sure to do the reshape, okay? So that it can be supported by linear regression. And then we do the train and test split. So it's as usual, And then you just call the linear regression to create the model. Then you call the fit to plug in training, that with the training data. And then you can collect the intercept and the coefficient. And for the coefficient, then in this case, because we have two features, so that's you are going to have two weights, is it W1 and W2, okay? And after that, you can use the testing data to do the prediction, okay? And the same thing, we can collect the performance. So this is regarding models performance, is it? And over here, we use accuracy, okay, to measure. And then if you take a look, you will see this model's accuracy, the performance is not good. It's just around 63%, as it compared with the previous 93, it's not good. And you can also do the predictor with some new data, etc. And this data set is regarding house price, is it, to predict based on the square foot and number of the bedrooms, is it? Okay, and that's regarding this implementation. And basically for over here, if you take a look at the original data, we miss the step of the data scaling part, is it? So maybe that's an exercise you can try, is it? After you do data scaling, where the performance be improved, is it? So we can try that. And the next part is similar. It's a raw implementation. Okay, raw implementation. And over here, the first part is to give some visualization, is it? And over here, because we have two features, is it? We have two features, square foot and the number of bedroom. And you want to find the relationship with the price, is it? So it's not easy to describe, to plot in a single plot. So that's why we have two subplots, is it? And one is regarding the relationship between size and price, and the other regarding number of bedroom, okay? And with the pie plot, then you can use the subplot, okay, to specify the number of subplots you want to have, is it, and how they are going to align. So here it says, okay, they are going to align the column. And then, so this is the subplot. Then for each of the subplot, then you can specify you want to do the scattered plotting and the label and the title and the tick, etc. And over here, it also raw implementation. With the raw implementation, over here, it shows us how to do we call it here, feature normalization, okay? So this is a mean value and this is a standard deviation, etc. And here it provides the function regarding how we do the normalization, and then it returns the respective value that you need, etc. And then over here, the next part is, did we do the normalization here, feature normalize? Yes. So over here, then you can do the feature normalization, etc. So then the feature can be normalized, bring to the same scale, okay? And the same thing, then you can call that cost function calculation. Is a gradient descent? We can still use the previous one. And you can also see the visualize the cost function versus the number of iterations, etc. And then you can also make the prediction. And let's see, this time it's still, is it the same one? So this time it's 16 1,650 number of square feet and 3-bedroom. The price it's 400 something K, is it? The previous one, did we do the, yeah, previous one, we do this, the same. You can see this two, the raw one and the one we use from SK, but we didn't do data scaling. The prediction, the result differs quite a lot. Okay, so that's why after class, maybe you can try to see if you do data scaling for the sklearn, where the result close to which to where is it? Yeah, where the result close to this. Okay, so that's maybe a good exercise. Okay, so that's for this first example. And then the second example is regarding polynomial. Okay, so let's take a quick look. And for this polynomial, we didn't use any data set existing, so we kind of randomly generated some data. Okay, and you can clearly see the target value is from some polynomial. Is it relationship with the features? Is it? And from this, so here is plotting of this, so scatter plotting of the data. And so for polynomial, how do we also borrow the linear regression? Okay, and here we also introduce two other metrics. One is the mean square error, and the other is the R2 score. Okay, and for X and Y, same thing. You need to convert, because for linear regression, it didn't take. We need to convert to 2 dimension, and then you call linear regression. Then you just directly do the fit, is it, and the predict. And over here, then we can collect the mean square error, is it? And what is the next one is the R2 score, is it? And generally speaking, in statistics, you know, for the R2 score, if it's getting close to 1, then that means it's better, is it? So over here, it's just a little bit over 50%, is it? So we can see that this simple linear regression is not a good model. Is not a good model. So can we try with polynomial? Is it so kind of something like this? X, then x squared, x cubed. Is it something? So plus like the coefficient. Is it something like this? So how are we going to do this polynomial? So in sklearn, then that can come from the pre-processing package. Then you import the polynomial features. Okay, with the polynomial feature. So here just try to show us an example. Okay, so here we have 1, 2, 3, 4, 5. Is it the value? And if you want to use polynomial models, then you needed to use this polynomial model to create the object. Then you specify the degree, is it? And in this case, the highest order is 2. So that's why we say, okay, degree 2, is it? And after that, then don't forget. So you needed to transform. Okay, transform. And then we have the polynomial, is it? So you have the x, and you have the x2 to the square term also, is it? So similar concept here, okay? So with regarding of x feature that we previously showed, is it? Here we are going to use the degree 2 polynomial, is it? And then we transform. So then this x, this time it's 2 features, okay? Not a single feature, is it? So x and x squared, is it? And then we do the linear regression, is it linear regression? And we can do a prediction. And we can also collect the R2 score, etc. And over here, we also do the scattered plotting. So let's take a quick look at the result. And then you can see the R2 square. This time it's improved from around 65%, is it, to 85%. So it's improved quite a lot, over 20%, is it, when we use a polynomial in this case, okay, in this case. But later on, we will also learn that it's not always a better choice. If you do the polynomial, okay, then it may also cause overfit. Okay, if you think, okay, based on limited number of training samples, you say, oh, the pure linear one doesn't work well, then you increase it to polynomial, then the result sounds good, is it? But later on, when you bring the new data, you do predictions, then the result may be bad. Then that's a case of overfit. And what over here it's explain is we also can do the sorted values. Okay, sort x values that before the plotting. Okay, before the plotting. So over here to do it is we also first needed to generate a sequence of pairs. How to do that? If you recall, in Python, we learned the zip function, okay, zip function. And when you do the sorting, you can specify which axis you want to sort, is it? So this is x and the predicted value, is it, regarding the polynomial. But then later on, you need to draw, is it? So when we do draw, that's why we needed to unzip, is it, the sequence of pair, is it, to their discrete values. So then when we do this plotting, because it's already sorted, okay, so that's the so this example discuss regarding polynomial. So after you apply the polynomial, then you can continue just to, in this case, it's still linear regression, is it? And this is, we still consider linear regression is because, so beta 1 and then beta 2, x2, is it? Then it's kind of, you view this as x plus beta 1, x1 plus beta 2, x2. So you treat x squared to a new feature. Okay, that's why over here we still use linear regression. Is it? It's just a linear regression regarding multiple variables. Is it? So it's a multivariate linear regression. Okay, so that's why here we can still use it. Okay, so we finish both examples today.